Okay, so today we are covering calorimetry, and calorimetry is going to be one way that we are using to find the heat of a reaction, your Q or your delta H. So the big picture, and I've written on the board here, ways to find Q or delta H. That's what we're doing this entire unit. This is going to be our first way, using calorimetry, and this is an experimental method for finding Q and H. So there are two types of calorimetry that we're going to cover. We did one in pre-AP and regular chem last year, so we're going to introduce a new one called bomb calorimetry because it's the bomb. I always say that and people think I'm stupid. So the first type, which is coffee cup calorimetry, since it's open to the environment, it's considered constant pressure calorimetry. Okay, and our other type is called bomb calorimetry, and this is the calorimetry used commonly to find calories in foods. Okay, foods undergo bomb calorimetry to make that happen. This is in a rigid sealed container, so it's not constant pressure. What would it be? Constant volume, correct. Okay, so let's take a look at, I'm just going to kind of give you the outline of each of these types. And then we'll work some problems. So coffee cup calorimetry, it sounds silly, but it's actually done in a styrofoam coffee cup. Why do you think we use styrofoam? Say it again? Yeah, it doesn't lose the heat. And it kind of does, but not as significantly as like a ceramic coffee mug would or something like that. So you have your coffee cup, and then you've got a thermometer inside your coffee cup. So what you're actually measuring is the heat after you mix two reactants together. So let's say I put in, I'm just making stuff up, sodium hydroxide solution and HCl solution. And I put in 50 grams of each of these solutions. So I'll either be given the grams of the liquid, or I'll be given the volume and the density, and I have to find the grams of the liquid. Okay, and I mix them in here, and this reaction is exothermic, so it gives heat off. Heat, go to the thermometer, and what happens to the temperature on the thermometer from initial to final? It goes up since it's given off, if it is giving off heat. Okay, if it's exothermic. So what we can do simply is use the equation Q equals MCAT to figure out how much heat is given off in the reaction. Our mass will be the total mass, meaning both reactants added up. If you have a liquid and a solid, you would add the liquid to the solid mass in your total mass. Your C is going to be the specific heat of the solution. Normally, they're going to tell you the solution in this problem has the same specific heat of water, and then you can use 4.18, but they will tell you. If not, they have to give you the specific heat of the solution. And delta T is your final minus your initial in degrees Celsius. And that's it. And you solve for Q. Okay, I'm going to show you, I'm going to write this down right now, the actual heat of the reaction, the actual change in heat of the reaction is equal to the negative Q. Doesn't make any sense right now. I'm just jotting it down, and I'm going to explain why in a second. You have to change the sign on your Q. One other assumption that we made, notice I said that all the heat's going to the thermometer here, right? Sometimes heat is not totally absorbed, and the problem mentions the fact that heat leaves. So we might have to add an additional step, depending on the problem. And we have to take into account lost heat. Might have to account for lost heat. And this is in both of these types, so I'm writing all the way across. Instead of Q equals MCAT, we use CAT with a capital C, not with a little c, the big fat capital C. And I will explain that when we actually get to problems. Okay, so that's coffee cup calorimetry, pretty simple. We then run into what we call bomb calorimetry. Bomb calorimetry, you've got two kind of containers. You've got your outer container, and the inner is the bomb. Okay. Let's say, you see up there I have a Snickers bar. I always blow up Snickers bars. Not in real life, in class I blow up Snickers bar. So if I wanted to find the caloric value of a Snickers bar, or any nutritional scientist would. You place whatever sample of food into the inner bomb of the bomb calorimeter. Okay, this is submerged in water. Then you have your thermometer in the water. This is hooked up in a way with ignition settings where we will ignite the sample and it'll combust. What happens when this combusts? It gets hot, right? As it gets hot, the heat goes through the calorimeter. What is the heat heating up here? The water, right? So when you do your Q equals MCAT, we only use the mass of the water. Why do we only use the mass of water? Because it's the water that's changing temperature. We've combusted to smithereens that Snickers bar. So we use the mass of the water, we use the specific heat of water, and we use the delta T from the thermometer. Well, what does that tell me, that Q? That a Snickers bar has so much heat? Well, we have to make this number actually more meaningful, because maybe I had a mini Snickers bar in there, right? But what if I put like the king size in there? So to make it meaningful, I would take that Q and I divide it by grams of Snickers bar or moles of Snickers bar, usually per mole, to make it a meaningful number that can apply to everywhere across the board. So the main difference is the use of your masses and your specific heats. This is only of the water because it's the water that's changing, and then we apply by dividing by the moles of the Snickers bar. Here, we're actually measuring the actual reaction, so we use the mass of the reactants. Kind of got it? Now let's apply it in problems, and I think it'll make a lot more sense. So go to your next slide. And here is our first example. When 1.095 grams of sodium hydroxide is dissolved in 150 grams of water, initially at 23.5 in a coffee cup calorimeter, the final temperature is found to be 25.32. Calculate the heat liberated, and I want you to add to this problem per mole of NaOH. It's going to make the problem make more sense. When NaOH dissolves in water. There's some good things here. Assume the specific heat of the solution is the same as that of water, so that gives us our C. And this is like the best news ever. No heat is absorbed by the calorimeter. When you see that, you should be having a party, because it's an easy one-step problem. So we have our calorimeter, and you don't have to draw this every time you do a problem. I'm just doing it until you get used to the concept of it. You have your coffee cup, you've got your thermometer. What did we put in our reaction? 1.095 grams of sodium hydroxide into 150.0 grams of water. We know our temperature initial and final, so we just use MCAT. Now this is an exothermic process. All right, so predict the sign on Q. If it's exothermic, it's going to get hot. When you put sodium hydroxide in water, and I can show you guys next time I make up a batch, it gets super duper hot. What's the sign of our Q? What should it be? Negative. Okay, so keep that in mind. So if we're going to do Q equals MCAT here, we are going to plug in mass, and it has to be the total mass. So we're going to add 151.095, yeah, 095 grams together. Do you see that? We're adding that and that. What do I do for specific heat? Use water, 4.18 joules per gram degree Celsius. Delta T is always final minus initial. What's our final temperature? 25.32 minus 23.50 degrees Celsius. So let's pick, I think we can actually go 4 sig figs. Q to 4 sig figs. So they got last period. So the answer so far is not negative. How did you get a negative? Hold on, I'm going to address that. Positive 1,149 joules. That's what this is telling us right now. But we know, based on the fact this is supposed to be exothermic, that we got a problem. And so remember on the board I wrote the delta H, the heat or enthalpy of a reaction, and we'll talk more specifically about enthalpy tomorrow, is equal to the negative Q. What's going on here is we're looking at this from the perspective of the thermometer. What did the thermometer do with the heat? It absorbed the heat. That's why this is coming out as positive. So anytime you use a thermometer, you have to change the Q to delta H by changing its sign. Anytime a thermometer is used. Okay? So, that being the case, our delta H of the reaction is actually negative 1149. But we're not done. What am I missing? What did I add to the problem? Per mole. So we have to make this per mole of sodium hydroxide. Currently, we know joules per gram, right? How many grams of sodium hydroxide was this representing? 1.095 grams of NaOH, right? So that's joules per gram. Do you see how I set that up? Okay, so we actually want to get joules per mole. So now we just do our little simple dimensional analysis. 40 grams, I got that from the periodic table, per 1 mole. And that'll give me negative something something joules per mole. Yeah? So negative 42000. If we want 4 sig figs, we can. And I'm sure there's a rounding in there. It's probably numbers in here, but we're just going to go with this just like that. So that would be our final answer. Okay, we're going to do another coffee cup calorimetry problem. It looks a little more confusing, but it's really no different except for one aspect. One thing that should jump out at you, notice it says nothing about assume no heat is lost, and it gives you heat capacity of the calorimeter. When you are given heat capacity of the calorimeter, you need to go cry. You need to cry, basically. And I was actually going to write, oh boy, here. Oh boy. Okay? Kind of like with Dalton's law, you went ugh. Same thing here. So what's happening, you've got your thermometer, and you've got heat from the mixture of liquids going to the thermometer, but you've got heat leaving. How much heat leaves is based on whatever specific material this calorimeter is made of. Every calorimeter has its own heat capacity. So once we find Q equals MCAT, we're going to have to add a step where we'll figure out how much heat is absorbed by this, and then add those two together. So first, let's use Q equals MCAT. So what is our total mass of reactants added? We're adding 50 grams to 50 grams. So we have a total mass of 100. They're going to give you molarities to be mean. That's totally extraneous information. So don't let it freak you out. The specific heat, can we assume water? Nope, it tells you the specific heat of the solution, 4.20 joules per gram degrees Celsius. All right, temperature final is 23.65 minus temperature, no, 25.40 minus temperature final initial of 23.65. So what happened? It got hotter, right? So again, this is supposed to be exothermic, so we better get a final answer that's negative. Upon first calculation, though, our Q here is equal to what? I got 735 joules, correct? 735 joules. Well, that only accounts for the heat that went to the thermometer. Because we have a specific heat capacity, we have to add. This is step 1. So let's go ahead and do a step 2, where we find the heat lost. To find heat lost, I wrote on the previous slide, Q is equal to capital C AT. This is easy, even if you don't memorize Q equals cat, because I don't like memorizing things, just look at the units of the specific heat capacity. It's 65.0, look, joules per degree Celsius. For every degree Celsius, this calorimeter absorbs that many joules. How do I get rid of degrees Celsius? I multiply by your delta T, which when we do this is 1.75. it's 1.75. Do you see how that leaves me with joules? That's how much is absorbed by the calorimeter. And that came out to be 114 joules. So what do you think I do with those two numbers? I have some that went to the thermometer, some that went out. How do I find Q total? Add them up. Equals 735 plus 114. So my Q total is equal to 849. But what's wrong? It's not negative. We said it was exothermic. So remember, delta H of the reaction then is equal to negative 845 because negative Q is equal to delta H. And it's joules. Okay, speed bomb calorimetry. 6 minutes to do this. We're going to find the caloric content of sucrose. Okay, we have our bomb calorimeter. We got our outside container, our inside container. Our sucrose is in there. There's our water. We are reacting 2.75 grams of the sucrose, and it's combusted with excess oxygen in 4.80 kilograms of H2O. It tells us that the delta T, it gives it to us. It says it's changing 2.01 degrees Celsius. So we've got enough here to solve for Q equals MCAT, but you should see an oh boy here. What's the oh boy? It tells you that the heat capacity of the calorimeter is 2540, and it's joules per degree Celsius if you want the units on that. So let's start with our step one. Our step one is to find how much heat goes to that thermometer. Okay, so that's using Q equals MCAT. And remember, we're just looking at the water right now. The water is what's changing temperature. The sucrose grams, well, we'll take that into account at the end. Right now, we're just going to go ahead and put our mass in grams as 4,800. I'm kilograms to grams of water. Specific heat of water is 4.18 joules per gram degree Celsius, and our delta T is 2.01 degrees Celsius. Our Q then turns out to be 40300 joules. All right, well, that's heat that went to the thermometer. Okay, now let's look at the heat that's actually more or less, it's absorbed here mostly, but then some can be absorbed from the outer as well. The heat capacity covers the entire instrument, so it takes both into account. And so our step two then is just taking Q equals capital C. That's heat capacity times the change in temperature. Our heat capacity is 2540 joules per degree Celsius. We're going to multiply that by the delta T. That gives us a Q lost of 5105 joules. So how do I find my total Q? Add them up, and I get 40300 plus 5105 joules. It comes out to be 45405. Okay, but is that any use to us? Nope, because what am I blowing up? A little bitty packet of sugar or a whole big bag of it? We have to make it a number that's meaningful. So we're going to convert this to moles, and it tells us, and I totally covered it up. Oh, here, per mole of sucrose. So this is just joules. We got to convert it to moles. I really like putting it, right now we know how many grams this is. This is per 2.75 grams, right? So for every 1 mole of the sucrose, the molar mass of it is 358 grams, giving us 5.91 times 10 to the 6 joules per mole. But once again, we have a problem, which is what we got to change the sign. Anytime we use a thermometer, our Q, negative Q, is equal to the delta H of the reaction. And so in actuality, it's negative 5.91 times 10 to the 6 joules per mole. And I'll just add moles of sucrose for clarity. Okay, that's it. Tomorrow we're going to learn the next way to find delta H, and that's through what I call the flippy thing. The flippy thing, using heats of formation and heats of combustion.